at doing that. So the first thing we'll talk about is that gases kind of have their own chapter where liquids and solids are they're left out, because gases can be compressed into a smaller volume. Liquids and solids cannot be compressed into a smaller volume. Okay? Now, their volume can change due to temperature going up and down, but you can't compress them at a certain temperature into a smaller space. Unless there's gas spaces in there, like a sponge. A sponge you can. You say, well, a sponge is solid. No, it's both a solid and a gas. Okay? So there's some mixtures or combinations of both solids and gases, and so you can make them smaller because they've got gases and they can crunch down. But if you have a solid in only the solid state, you can't compress it into something smaller. Okay? So gases have their own laws, and we look at a bunch of different variables that will change in a gas, that will change some of its other characteristics. So the first thing we're going to look at is how we measure a pressure. So the question is, what is pressure? What is pressure? Do you guys feel pressure ever?
Am I talking like with school? I feel pressure.
Yeah, you feel that pressure, and a lot of pressure you put on yourself. There are some students I have in class, they have no pressure because they don't care about school. They don't care about grades as long as they're passing. And they can graduate and get out of here. Okay? But pressure, a lot of pressure is what you do put on yourself. Now, I know there's pressure from parents to get certain grades, but some of you are like my kids, they put more pressure on themselves than what we put on. Okay? And so then that creates anxiety, pressure, and that's why some students have a tough time with tests, because they feel that pressure and they got anxiety, and man, they can't think very straight. So, but this pressure is a physical pressure. Do you know what's involved with this type of pressure? What other units can we use to describe pressure? Now, some of you are going to give me units of pressure. I don't want units of pressure. I want the units that make up pressure. So do you guys know of units that make up pressure? So when you think of you putting weight down on the ground, you're putting pressure against the ground. So kind of that. We won't call it mass because it involves gravity too. So it's the weight. So it is kind of mass, but my pressure I put on the ground here versus the pressure put on the moon or somewhere else is less gravity. We have the same mass. I'll have the same mass, but the weight's going to be different. So what's another unit or another way of saying weight that's better in physics and chemistry? Instead of weight, we say, starts with an F. Force. Okay, gravity is a force. So pressure involves a force. Does anybody know the units for force?
Newtons.
Newtons. Now, I won't have you guys use this equation other than us talking about what pressure, what pressure is, and then we're going to apply different units to that. But force is in newtons. Now, one newton is about a fifth of a pound. It's about 3 ounces. 3 weighted ounces. Okay? It's about 1/5 of a pound. Okay? Or I could say 0.2 pounds. Okay? Now, that Newton force, you can't just have force or else force and pressure would be the same, and they're not. So what else do you have to have? And you said it, Eric, I think you said area. So you have to have an area down below that it's being applied to. So it would be, in our area that we're going to use is a meter squared. So if I got a Newton over a meter squared, that is a unit of measurement that we're going to not have, we're going to have just one unit for it that describes it. Okay? It's kind of like molarity, right? You can put a capital M or you can put what? MOL over liter. Okay? Same thing. So that's newtons over meter squared. So if you have a container and it has a gas in it, that gas spread out and it's moving. You guys don't have to draw this if you don't want to. You guys will do your own drawings here in a little bit. Now, the arrow represents a vector. You guys ever do vectors?
Physics.
Okay. If you've done physics, then you know what the arrow stands for. What's the arrow stand for?
Direction.
It stands for direction and its
Distance.
velocity, right? Relative velocity,
Yeah.
right? So the longer the arrow, what do you know about its velocity?
It's higher.
It's faster. So if I make a big long arrow, now all these arrows, if they're at the same temperature, are going to be the same length. So if all these are going all different directions, but guess what? If it's just one type of atom in there that makes up that gas, let's say neon or helium, they're moving, and they're moving with a speed in a certain direction, but once they hit the side of the container, they bounce off and they go a different direction. So they're all moving. So how do we measure? So pressure is going to equal force over area. So where's the force come from? If I'm measuring the force of these particular atoms, where's the force come from?
Is it how fast they're bouncing off the walls?
Right, the collision. The force is the collision. The average collision. Okay? So they're moving along and they collide with the side of the container. That applies a pressure there. Okay? And then we got another one. It hits the side of the container here. Not all simultaneously. They're all doing it. Now you got to realize there's probably a trillion atoms in here. Not 5 or 6. There's a trillion. So there's probably a lot of them hitting simultaneously on the side of the container. On all different sides. Top, bottom, both sides. So the pressure in there is the same everywhere. Okay? So the forces that... then the area would be the space they take up when they hit. Alright? So when they hit, and when you add them all up, I suppose if you add up all the forces of all those collisions by the area, and keep doing that, then you get your overall pressure. Right? Okay? So, it's nice to know what pressure is, because a lot of times we go through this and students' pressure is just a number and they don't have a clue kind of what's going on. So, that's pressure. Alright? Now, what if you don't have anything in here? It's void of anything. Then what do you know about the pressure? Inside there, what do you think the pressure is going to be? 0. Right?
Yeah.
There's no collisions, so there's no force. So what do we call this when we don't have anything in a container? What do we call the state of that? Do you know? Vacuum. It's a vacuum. All right?
Wow.
So,
That's really just my first
so then if you have void of anything, that's what pressure? Zero pressure. Can you get negative pressure? No such thing as negative pressure. Okay, you can have a difference in pressure, but you're not going to have a negative pressure. So, any questions yet? Now, this size of this container represents a volume. And so later on, when we take a look at it, it doesn't represent an area, but it represents a volume. So pretty soon we're going to go ahead and, have containers that we're going to have. Terrible at writing, doing something three-dimensionally. So, okay. How's that go? There, over. Okay, something. So inside there, we're going to have, inside that container, we'll have molecules moving around, and that's a volume. Okay, that we're going to have. So we're going to talk about volume 2. We've already talked about another condition that we need to talk about. You remember what the other condition was? The size of the arrows they represent. Speed. But what else can they represent?
Direction.
Direction. What other? So how can I measure that speed? When I put an instrument inside here, how could I measure that speed? What would be an instrument that I can put in there? I can measure how fast they're moving.
A thermometer.
Thermometer.
So temperature.
Right? Temperature. Temperature measures their average speed. Okay? And do you guys remember what the temperature we have to use? Kelvin. Okay? We have to start, because Kelvin you have to start, you gotta have to start where where particles are not moving. So we got pressure, we got volume, we got temperature, and something else I had in here, in that container, were particles. What do you think, what other property, the last property that we're going to talk about when we talk about gases? So we got pressure, volume, temperature. What would we represent here when we put these particles in there? What do you think that represents? So what's a way of representing a number of particles? What unit? We use it all the time. Nobody else uses it. It's only for us in chemistry. Moles. So these dots here could represent a number of moles. Okay? And if I get more and more of them in here, what do you think happens to the pressure?
More.
Yeah, I got more collisions. Okay, I've got less of them in there, I got less collisions. And so that's kind of that idea of kind of understanding. If you notice, it takes the space up of the whole thing. So I'm going to talk about ways in which to measure pressure here. That's kind of a thought process I want you guys to think about when you think about pressure. Pressure is force over area. So if you're going to increase the pressure, you're going to get more force. What's going to create more force? You got to think about what type of things create more force. Okay, temperature, size of the arrows. The longer they are when you draw them, the faster they're moving. Volume, of course, the size of the box that you draw would be your volume. And then how many you put in would be the number of moles that you have. Okay, so think about those things. So then we've got this thing called a manometer. Okay, we got what's called an open manometer and a closed manometer. Okay, what's the difference? Well, let me show you one way to measure pressure, atmospheric pressure, is with a barometer. Okay, you don't need to draw this. So we're going to take this glass tube and we're going to fill it up inside. We're going to fill it with mercury. and all the way to the top. And then what we're going to do is we're going to dump it upside down into this bath of mercury. So this is Hg. We dump it upside down. If it's tall enough, we're going to get a gap in the top. If it's tall enough. If it's not tall enough, we won't get a gap in the top. But if it's over probably 3/4 of a meter, it's going to give us a gap, because what happens, this mercury is really, really thick, 13.6 grams per milliliter is what it is. And so air pressure on the outside cannot support that whole column of mercury. So here's the air. So here's the air particles. Okay, and they're moving all over the place, but these specific ones we'll say are moving down here, and they hit here. Hit here. They're hitting all the air's hitting there, bouncing off, but they continue, more molecules hit. They hit, and they create a pressure that forces that mercury to stay up in its column. But it can only stay up so high, and so it leaves a gap here. And what do you think that gap is up there, where there was mercury at one time?
Air.
Nope.
Water.
Nope. What's void of anything?
Vacuum.
Vacuum. So there's a vacuum up here. There's a vacuum there. There's nothing in there. This is void of anything up in this, because it was mercury, but then it came down, but there was nothing that replaced it. So at this height here, they have what's called standard pressure. So who came up with this idea of standard pressure? Well, somebody at sea level, where sea level would be level of the ocean when you're there. They kind of use that as a standard pressure, and they kind of got an average what they think that is. You know, of course, with weather, it always goes up and down. Okay, you get a high pressure, low pressure, but they came up with a number, and I still don't know how they came up with it, but they say that standard pressure is a height that would be 760 millimeters in height. That's the height of it. So this is at sea level. Okay.
Do I need to know 760?
You will. You'll have that ingrained in your memory again, because at one time you did have that already. Okay, so what happens when you're not at sea level? Okay, let's say you go up in altitude. What happens when you go up in altitude? What happens to the air particles?
It's thinner.
Gets thinner. What does that mean about moles?
It's a little less.
Less moles, right? So now we have less of these hitting. They might be hitting with the same speed, but guess what? We got less of them. We got less of them hitting compared to the time before. There's a bunch hitting. Here you don't have as many. What happens to that level of mercury?
It's a fire.
So this mercury's kept up there with the force of air.
So it's small.
So it's going to go down, right? So now it's going to go down because now there's less air supporting it. So now it's going to go down. It's not going to be as high. So now it might go down to, say, 720. What if you keep on going up in altitude?
It's going to get lower and lower.
And get lower and lower and lower. Okay? So you got less and less molecules pushing down. So the mercury goes down. Well, what if you go like below sea level, like Death Valley is below sea level?
Then it's gonna get higher.
So it's going to go higher. Because there's more and more particles as you go below sea level. So, okay? Any questions on that? So that's kind of what that's called a closed barometer, and that's kind of how it works. And that. So, last thing I'm going to show you is they have these manometers here, and they've got an open and closed manometers. Okay, this is kind of like a closed manometer in a way, but it's measuring the pressure of the air. So this is called a barometer. So then in your book you have some drawings that represent what we call manometers. And I won't reference this too much after this. When we measure it, we have a digital pressure gauge that we use. We don't use the old-fashioned manometers to measure pressure. Okay? So this first one's a closed manometer. So it's closed off from anything on the outside. So this first one that we have
Do we need to draw this?
No. No. Okay. So this has got a gas in it. Down there. So that's got a gas in it. And so this has got mercury here. Okay, so right now this is closed off, and the difference between these heights, we don't have any difference between them. So that tells me that there's probably no gas in here. Now I said that there's a gas in there, but let's say there's no gas in there, it's a vacuum, then that mercury would be at equal heights. Okay? So now we're going to put a gas in there. Okay, what do you think that's going to do to that mercury?
It's gonna get higher on the left side.
Yeah, very good. It's going to get higher up here, and it's going to get lower on the other side. It's going to get lower here. Okay, so now we've got a level. Now we got a level here and here. And the difference between these two have a height. So let's say that height is 20, say it's 20 millimeters. Okay, so what's the pressure of the gas? 20 millimeters. 20 millimeters. Okay? So let's put more gas in. What happens to the column? It goes up more, right?
Yeah.
So it goes up. This side goes down. And then the difference is greater. So then the height difference is your pressure, right? So now let's say it's 80. How many more particles do you think I put in there if it went from 20 to 80? Any idea? Anybody want to take a guess? 16? You say? Would you say 4?
Well, I was just gonna say like 4 times as 4.
It's 4 times as much. Right, because we got 4 times the collisions now. 4 times the pressure. Okay? So then if I take out, then it would just switch the other way, right? Okay. Does that make sense?
Yeah.
Okay. So then we've got this open manometer. Okay, what's the difference between an open manometer and a closed manometer? Here's the difference. Here's an open manometer. Okay? And so we got mercury in there. And there it's equal. Let's say it's equal. And we've got these particles in here. What is it? What's the pressure inside being compared to?
The outside.
The outside pressure. So if the outside pressure is 760 and they're equal, what's the pressure inside? 760. Make sense? Now, the closed manometer, that would be what? 0. Okay? But since it's a... Oh, so it's always comparison to the outside pressure, whatever it is. So if the outside's 760 and we've got a gas in there and it's up over on this side and the difference is, say, 20 in height. What's the inside pressure?
780.
780. Where before in the closed it was 20. Does that make sense?
Yeah.
Okay. So that's what difference between an open manometer and a closed manometer would be. Okay. All right. I just got a little bit of a similar thing that you guys have to answer questions on, and this 43 through 45 on page 209.
Are we going to turn this in?
We're going to be adding on to the assignment, so this would be just an add-on, and so page 209, 43 through 45.
I feel like we're backtracking, so we were already at page 299.
I know. I didn't want to, for some reason, I didn't want to do